Hello, my name is Satyajeet from the Department of Electronics and Communication, NIT Andhra Pradesh. In this video, we are going to discuss about the role of phase angle in image processing. Let's start by taking 2D DFT equation in polar form. The magnitude of the given expression is called the Fourier spectrum or the frequency spectrum. It is represented by the absolute value of f. The phase angle of DFT is represented by phi as shown in the following equation. In the given equations, r and I represent the real and imaginary part of f. Similarly, we can also calculate the power spectrum by the given equation. Now, let us take the zero frequency term of the Fourier transform. This can be achieved by taking u and v value as 0. We multiply and divide this equation with m into n, where m cross n represents the dimension of the DFT matrix. We can further simplify the equation 2 to equation 3, where f bar denotes the average of small f. From equation 3, we can clearly understand that the zero frequency term is directly proportional to the average of f. In many cases, zero frequency term is also considered as the DC term. As shown in the equation 4, we have calculated the spectrum of zero frequency term. From equation 4, we realize that the spectrum of zero frequency term is large, due to proportionality constant Mn being large. Hence, it ends up being the largest component of the spectrum by a factor of several orders. Let us take an example. For simplicity, we consider a rectangle, black and white image. Now, we find the spectrum of the image and scale it to the range 0 to 255 and display it in image form. As the origins of spatial and frequency domain are in the top left, hence we observe that the area near the origin contains the highest value. We also notice high values at other corners too. This is due to the periodicity property. As the image B is hard to visualize, we multiply the original image with -1 to the power x plus y and then calculate the DFT. This provides us with a different result as shown below, which is much easier to visualize. From image C, we can clearly see that DC term at zero frequency dominates the spectrum and the other intensities in the spectrum are compressed. So to bring out those details, we do a log transformation, that is 1 plus mod of f u, v. The result of this transformation is given by image D. Now, let us go back to the original image. In this image, we make a slight modification by moving the rectangle to a different position. As we know, the spectrum is insensitive to image translation, hence we get the same result. But if we rotate the original rectangle by a certain angle, this results in the spectrum to also rotate by the same angle. As we can observe, the original image is very different from the translated image. Yet, if we get the same resultant spectrum, then there must be a difference in the phase angle. We can confirm this by plotting the phase angle of the different images. As we can observe, there is a clear difference in the phase angle in the images in each case. But you must also note that there is a lack of any similarity. Hence, the general visual analysis of phase angle yields little to no information. So, from our observation, we can conclude that the spectrum of DFT provides the amplitudes of sinusoids that combine to form the resulting image. The large amplitude of any component in DFT spectrum implies the greater prominence of a sinusoid with that frequency in the image. Even though it might appear the phase component is less intuitive, it is important for understanding the displacement of sinusoid with respect to their origins. Hence, we can say the magnitude of DFT helps us determine the intensities in the image, whereas the phase angle carries the information about the location of the object in the image. To analyze the importance of phase in image processing through Matlab, our very first step will be to import an image. In the next step, we find the FFT of this image and we split it into spectrum and phase. In step 3, we scale the phase angle matrix from 0 to 255 in order to display it as an image. As we can clearly observe, the phase angle image provides no relevant information. In step 4, we have taken two cases, one in which the amplitude is equal to the amplitude of the original image and the phase is equal to 0, whereas in the second case we have taken amplitude is equal to 1 and phase is equal to the original image. Then we calculate inverse Fourier transform for both the cases separately. Step 5, we plot both these images. can clearly observe that the image reconstructed using the phase of the original image still contains the original dog, whereas the image reconstructed using the amplitude only contains the intensity values. We further apply histogram equalization on the image reconstructed using the phase only. This provides us with a clear shape of the dog. Hence, the result of this experiment also allows us to solidify our conclusion. Thank you.